So here we are, the last chapter of Unit 4. This one is on marine and coastal systems and resources. The marine biomes, the marine aquatic biomes that we did with the biomes books are in here, just like I did last chapter with the freshwater ones. We'll skip them, but I just wanted to make sure you guys had all the content there that you need, should you need to go back and find them. Okay. So these are the objectives for this chapter. We're going to look at marine pollution. We're going to look at ocean fisheries and look at how the oceans influence and are influenced by climate. That's a big thing that we need to make sure we get out of this. So a lot of the commercial fisheries around the world are in the midst of collapse or are very, very stressed. And the case study for this chapter that we're not going to do deals with Atlantic cod. Cod fishing became a huge component of economics in New England and Eastern Canada. But in the last 20 years, there's a lot that it's been overfished so badly that it's collapsed. And we're going to take a look at that in a little bit of detail. So it's a bottom-dwelling fish. You can see the fishing grounds, right? And all these times when they've closed, 1992, 1994. They brought in huge industrial trawlers, and we'll talk about what trawling is later on in this lecture. And they overharvested the cod. In the 80s, the trawling did so much damage to the habitat where the cod live. And then even into the early 90s, cod were at 10% of their long-term abundance. So they stopped fishing in Newfoundland off the Grand Banks. In Canada, they stopped in 1992, and then they did something similar in 1994 in the United States, and they still haven't come back very well at all. They're at about 34% of historic levels, which is okay, but it is not working well. The restoration is not happening well. So we've changed how we fish. We're fishing for these capelin rather than young cod to give the young cod a chance to compete and grow back. And then there's been some restoration of the seafloor, which, as you'll find out, trawling destroys the seafloor. So when the seafloor habitat comes back, then the environment will be better for the cod. So, Captain Obvious, the oceans cover 71% of the Earth's surface. They make up most of the hydrosphere. They influence the atmosphere and the lithosphere, and they encompass a whole lot of the biosphere. There's a lot of life down there at the bottom of the ocean and in the oceans that we don't really know too much about. The seafloor is not flat. There's a lot of topography, a lot of change in elevation. The deepest trench in the world, the Mariana Trench, is deeper than Mount Everest is high. So if you could put Mount Everest at the bottom, the deepest part of the Mariana Trench, there would be about a mile of water above the Mount Everest until you get to the top of the trench. Okay. They measure bathymetry for the ocean depths and topography. So you can see the mid-ocean ridges and all that stuff. And I'll pull up a map, a bathymetric topographic map of the ocean, and you can see that how detailed it really is. It's actually pretty cool. So we're going to talk about this later on. So I kind of wanted you guys, this is kind of a topographic bathymetric picture, cross-section of the ocean. So the part where you guys lay your blanket when you go to the beach is right on here. Right off the beach is the continental shelf. There's a point where the shelf gets steep. They call that the shelf break. And then the continental slope goes down into the continental rise, and then into the abyssal plain. And usually in the middle of the oceans, you've got these mid-ocean ridges. Trenches are there too, which create volcanic island arcs. But that is the last unit that we're going to talk about. Unit 7, I think it is. Wherever you have physical structures underwater, whether it's volcanism or a mid-ocean ridge or an island arc or a reef, you're going to have life. And that's where you tend to have the most productive areas for fishing. So we know ocean water is salty, but it is not that salty. Okay. Ocean water is only 3.5% salt. Most of it is water. Okay. So the salts happen when sediment runs off the land, and creeks and rivers and streams and all that, it all collects into the ocean. All of those creeks and all of those rivers and all of those streams bring the salt, and it concentrates there in the ocean. So that's why the ocean is salty. Streams are not, because streams don't have as much material flowing into it. When you have all of that water flowing into all of the oceans, the salt is going to stay behind as the water evaporates. So that's why the oceans are salty. The salt itself is mostly chlorine and sodium. So it's sodium chloride. There's some sulfates, and then trace amounts of magnesium, calcium, potassium, and bicarbonate. Bicarbonate is going to be really important down the line. And it varies. Typically, when you have warm water, surface water, it's going to be less salty. Okay, it's going to have a lower salinity. As you get further away from the equator, temperatures are going to drop. And you're going to have less precipitation, so more evaporation, and you're going to wind up with a higher salinity. Coastal areas are less saline because of the influence of fresh water running off. We know about nitrogen and phosphorus. They exist in the oceans. They lead to eutrophication if concentrations are too high, and you can have eutrophication in the ocean. They're important in nutrient cycling and in the sustenance of marine food chains. And they also contain dissolved gases. Ocean water contains dissolved gases. Oxygen is important. Oxygen tends to, and most gases tend to dissolve better in colder waters. All right. Carbon dioxide is also soluble in ocean water, and it can turn the water more acidic. That's a key thing that we need to make sure we understand, because ocean acidification is a thing. The penetration of the sun will determine life and temperature as well. It doesn't go very deeply, so typically temperatures decrease with depth. So the coldest, saltiest water is going to sink, and that's going to be important for whole Earth circulation later on in the lecture. The warmer, less salty water is lighter, and it stays at the surface. So it stratifies. The ocean is stratified. And you get the first 150 meters of ocean water, so about 400 to 500 feet of ocean water, is influenced by the wind and the sun. So that tends to have the same density. So it's the same temperature and the same salinity. But as you go down, you hit a change. Below 150 meters is something called the pycnocline. It's one of my favorite oceanography words, because I took oceanography in college. It's where density increases really rapidly. So it gets cold and it gets salty below the pycnocline. So what's below the pycnocline is really not affected by sunlight, wind, storms, and temperature fluctuations. It's really kind of quiet and still down there. Ocean temperatures tend to be more stable than those on land because water has a high heat capacity. So if you've ever been to the beach in like October, you can go in the water in October. It's chilly out on the beach, but it's a lot warmer in the water. The reverse is true also. So if you guys have ever been to the shore, like Memorial Day weekend, it's nice and sunny on the beach and you're comfortable out there hanging out on the beach in your bathing suit, but you go get in that water and it is so cold. You're like, man, what the heck was I thinking? So the temperature of the water will increase after the temperature of the land, and it'll stay warm after the temperature of the land has gone down because of water's heat capacity. So we can talk about the surface flow of water, okay? Water flows in river-like masses called currents. These currents are driven by differences in density, differences in temperature. So because of heating and cooling, they're controlled by gravity, and they're also controlled by wind. The surface currents that you see here are wind-driven currents, all right? And we're going to talk in the atmosphere unit, which is the next unit, I think, about the connection between these patterns of currents and the wind patterns. Surface currents are very fast and very powerful. The Gulf Stream, which is right here, this is what influences us. It moves at 2 meters a second. That's fast. And it takes this warm water over to Europe. So if you look at latitude-wise, right, Great Britain is roughly equal in latitude to Newfoundland, or a little north of Newfoundland, New Brunswick in Canada. It should be a lot colder and snowier than it is, but it's not because of the influence of the Gulf Stream bringing that warm water across. Currents took debris from the tsunami, the 2011 earthquake tsunami, and trucked it all the way across the Pacific Ocean. That's a piece of Japanese debris, kind of looks like a train car, that got washed off the tracks or wherever it was, made its way into the ocean, and washed up on a beach. It looks like the Pacific Northwest, Oregon, Washington, northern California. So ocean currents can move stuff. There was a study done when I was in college. A container fell off a ship. It happens fairly frequently from what I understand, coming from the Pacific to North America, Asia to North America, across the Pacific. And it had a bunch of Nikes in it, a bunch of Nike shoes. So they traced and tracked the Nike shoes to kind of determine the circulation, if the circulation had changed in the North Pacific. So we'll talk about that too. So vertical movement of water can also affect marine ecosystems. So water can move across the surface, but water can also move vertically. So as the wind blows north, in this picture, across north or across the coastline, there's something called the Ekman spiral. You don't need to know it. It's one of the things that I had to learn. The Ekman spiral, along with something called the Coriolis effect, are going to pull the water offshore. All right, there's the Coriolis effect. It's going to pull the water offshore. So the water is going to be, there's going to be a gap away from the coast. So what winds up happening, you can't have a gap in the water. So water has to come from below, right? The water wells up to replace that water that's being blown off, that is moving offshore. So that cold, nutrient-rich water comes up. And where there are nutrients, there's a lot of life, okay? So that's where you see lots of fish. So upwelling is going to bring warm or cold, nutrient-rich water up. The opposite of that is downwelling, okay? Downwelling is where you have what amounts to a pile of water at the surface, and that pile of water at the surface can't stay at the surface, so it sinks. So it takes surface water and buries it deep. When we talk about the chemistry of the ocean, the good thing about that is that it takes carbon dioxide from the atmosphere and buries it down lower in the ocean. Okay, so there's dissolved oxygen coming, and then it is going to bury that carbon dioxide down deeper in the ocean. So we just talked about surface currents and we talked about vertical currents. You can put them together to get something called thermohaline circulation. Okay. Thermo is temperature and haline is salinity. So it's circulation based on differences in temperature and salinity. So you've got warm, lower saline water moving across the surface, and saltier, colder, or denser water is going to move horizontally. And it creates a conveyor belt type movement that really is responsible for regulating a lot of the surface temperatures of the Earth. So we're going to talk a lot about this. I'm going to explain it here, and we're going to go back and explain it again. So the surface currents are in the red, and the deep currents are in the blue. So this is the Gulf Stream, right? The Gulf Stream runs up the east coast of North America, and it's warm. And as it gets up to the top here, okay, up to the northern reaches, it's going to cool down. And it's going to cool down, and it's going to sink, right? So it's going to take that, the Gulf Stream is responsible for taking this warmth, right, and spreading it all up the east coast and even over here, and then it's going to sink because it becomes colder and more dense. And then it's going to circulate and make its way back up. And you can actually trace this water as it goes through the oceans because it's got a distinct temperature and salinity. It's going to come back up as the topography of the seafloor changes, and then allow it to keep moving thanks to sunlight and wind. One thing that's changing here, where the water called, you don't need to know that it's the North Atlantic deep water, where this North Atlantic deep water sinks, as the climate is changing, okay, it's causing glacial ice to melt. Ice does not have salt in it, okay? Ice is fresh water. So if you are introducing more fresh water from Greenland and other continental glaciers melting, it's going to dilute this salt water. So if this salt water dilutes, it's not going to sink as rapidly, which means the Gulf Stream is not going to move as rapidly, which is going to have impacts on us here on the East Coast. But we'll talk about that again. El Nino. This is a big thing. It's called the El Nino Southern Oscillation, or ENSO. It's a change in atmospheric pressure, sea surface temperature, and ocean circulation in the area along the equator in the Pacific Ocean. Okay. So these are normal conditions. Typically, the winds, as you see here, move from the eastern side of the Pacific over by South America across to the western side of the Pacific, over by Australia and Indonesia. So it's the equator, so this surface water is warm, right? So as the wind pushes across the ocean, it's going to take the water with it. So all of this warm water is going to get pushed because the winds are pushing it, and it's going to pile up on the Indonesia side, on the west side of the Pacific. Okay, so there's a net movement of water across the Pacific towards Indonesia. So what's got to happen, right, in order to replace this water that's being pushed to the west, water has to well up. There's upwelling of cold, deep water. So what you wind up getting here is a lot of fishing grounds, right? You've got anchovies that are a huge part of the fishing industry in Peru. And they rely on this upwelling because it's cold, nutrient-rich water, and the anchovies love it. So that's a normal situation. You've got the western side of the Pacific by Indonesia is warmer. The eastern side of the Pacific by Peru is colder. As long as these winds are doing what they're supposed to do. They're called the northeast trade winds, by the way. Okay. What happens sometimes is these trade winds don't blow as hard as they were supposed to in the direction that they were supposed to. Air pressure changes, okay? So these winds don't blow as hard in the western direction. If they don't blow as hard, the water is not going to stay piled up over there, okay? So what's going to wind up happening is that this water, think of it like sliding down a hill in sledding. This water is going to slide back. It's going to go back down the hill, and warm water is going to be off the coast of Peru. All right. So the Eastern Pacific is warmer than normal, and the Western Pacific is cooler than normal. So there's no upwelling. The upwelling doesn't happen. Okay. So it stays, the cold water stays below. So you're going to have impacts and influences on fishing because the anchovies and the fish that the Peruvian people fish, they love that cold water. Okay. It's going to also impact weather conditions, and we're going to talk about that. The La Nina is the opposite of El Nino, okay? A La Nina, I'm going to go back to this, is when these winds blow even harder to the west, right? The trade winds get stronger. So when that happens, this side, the western side of the Pacific, gets even warmer, and the eastern side of the Pacific gets even cooler, okay? Cycles happen every 2 to 8 years. We can take a look at if we are in an El Nino now or what's going on. We're looking, and this is a big area of research for oceanographers and meteorologists to kind of see if that pattern is changing or not. We don't have to dwell very much in this, okay? Because these are the marine and coastal ecosystems. So talks about the photic zone, pelagic. Benthic is a word that I'm going to use. Benthic means bottom dwelling, okay? So the intertidal, this is all part salt marshes. We need to make sure you guys understand those. Mangroves, okay? There are some really specific things that they want to know about mangroves. I'll tell you guys a story about mangroves when we get together. Let me write that down. So they're really salt tolerant trees. Their roots don't really extend far into the sediment below because the sediment is anoxic. So their roots kind of stick up. And you can see in the picture here that the roots themselves become habitat for lots of organisms, right? Like clams and all that stuff. Snakes even live in there, lots of fish. And that'll be part of the story that I tell you guys. So they're a really important coastal ecosystem. They're threatened by a variety of anthropogenic sources. These are the things that you need to understand about the mangroves, okay? They are clearing the mangrove forests for commercial development. They are building dams, which is reducing the flow of the water to the mangroves. We're overfishing in them. They are susceptible to pollutants from agriculture and industrial waste. So those are the ways that, we are damaging the mangroves. We learned about estuaries, kelp forests, the coral reef themselves. They're really, really pretty. Coral bleaching is when the zooxanthellae, which are the algae that live symbiotically with them, they die. And then if they die, then the coral doesn't have nutrition because it's a symbiotic relationship. It's happening more and more frequently when corals are stressed by increased water temperatures and elevated pollution levels. There are some pretty stunning statistics about what's going on in the Great Barrier Reef in terms of coral bleaching. Not so much due to pollution levels, but due to increased water temperature. We don't need to talk about that. So a lot of the pollution that's getting into the ocean is non-point source. So it's coming from watersheds that wind up making their way into the ocean. There's so much plastic in the ocean. It's kind of ridiculous. Okay, we're also getting more nutrient pollution and eutrophication, as we talked about with the Gulf of Mexico and the Chesapeake Bay. This makes me sad. So, whether it's bottles or straws or anything, marine creatures can get entangled. They can ingest it. That's an albatross, which makes me very, very sad that this is happening. Yeah, it's awful. So ocean currents concentrate floating plastic in the middle of their circulation called gyres. The North Pacific Gyre contains something called the Great Pacific Garbage Patch. where there's more plastic than organisms. And a lot of those plastics are microplastics rather than big pieces. I mean, there are big pieces of fishing nets and bottle caps and all that stuff. But a lot of it is microplastic that actually bioaccumulates and biomagnifies in living organisms. They are important in the introduction of invasive species. You could have, organisms that attach to these plastic pieces, and then they spread through the action and motion of the currents, and you can have them introduced in places, and they can become invasive species. Probably, I'd say around 2012, 2013, they be like scrubbing body washes and stuff had plastic microbeads. And even in toothpaste, they had plastic microbeads that, we would rinse down the sink after we washed ourselves or brushed our teeth, spit it down the sink. They were accumulating in the ocean. So we have since banned them, which is good. Oil pollution is another thing. I remember the Exxon Valdez. I was in 8th grade or 9th grade when that happened. I think it was in 8th grade. And I remember seeing pictures of all the wildlife just covered in oil. I also remember Deepwater Horizon, and I can show you guys pictures about both of those things and some of the issues with it. So we don't have really big oil spills, but they are big issues when they happen where they happen. Okay, they cause a lot of damage in the immediate area. But about half of the petroleum products in the ocean are there from natural processes. Oil and petroleum products seep out of the ocean floor naturally. Okay, but it's not all at once. It's not a huge chunk or a huge volume of petroleum coming out of the ocean in one spot. So it's a little bit here and a little bit there. But there is natural oil and petroleum products in the ocean. So they have, since the Exxon Valdez, they have improved engineering of the ships, and they've also improved the cleanup. So all tankers in U.S. waters have to be double hulled. So they have to have two hulls to prevent the leakage. It wasn't that way before the Exxon Valdez. There are toxic pollutants that can contaminate seafood. We know about mercury. Lead is another toxic pollutant that can make its way into seafood. Okay, so mercury gets into the ocean from burning coal. That's the biggest way. Mine tailings and some other sources. Mercury bioaccumulates and biomagnifies like crazy, which is why when I was pregnant with Aaron, I was only allowed to have 4 ounces of tuna like every 3 days. So I also wasn't allowed to have albacore because albacore has a higher concentration of mercury in it than the chunk light tuna. Swordfish and shark are also off limits to pregnant women. And you wouldn't know if you'd never been pregnant. All right, we talked about the dead zones and eutrophication. Sometimes those algae, when they bloom, they can produce, it's called a harmful algal bloom. And a lot of times when they close the beaches for swimming, it's because of the algal concentration, the toxin concentration in the water. So when they tell you not to go swimming, don't go swimming. And some of them produce a red pigment, okay, and it's called a red tide. This isn't necessarily toxic, but it's just gross, and people don't want to go in the water when it looks like that. But it's harmless. Okay, this is another big idea. So naturally, the oceans, as we talked about when we talked about the carbon cycle, the oceans are going to absorb carbon dioxide from the atmosphere because of the ocean atmosphere interface. It just naturally makes its way in. So this is pretty cool. About a third of human-generated carbon dioxide has been absorbed into the ocean. So the oceans are a giant sponge for anthropogenic carbon dioxide. But there's a capacity, there's a maximum amount of carbon dioxide that the oceans can absorb. Once it gets to that point, it's not going to be able to suck in and soak up any more carbon dioxide. So global warming is going to continue. All right. And when the ocean absorbs carbon dioxide, the pH of the water actually decreases through a process called ocean acidification. Again, this is something we're going to talk more about. We're going to go over more slowly when we talk about it. So if the pH of the water drops, right, and the shells of the critters that live in the ocean are made out of calcium carbonate, which is basically like Tums or limestone if we go back to the cemetery lab, if the pH drops, then those shells are not going to grow as well. Coral is calcium carbonate, so coral isn't going to grow as well either. Okay, so there you go. That's that last part. Acidification makes carbonate less available. We're going to talk a little bit about the chemistry of that. And you can look at this picture right now. Okay, if these are carbon dioxide concentrations in the atmosphere. So if carbon dioxide concentrations are 280 parts per million, you see a lot of areas where reefs are growing. You see a lot of these cooler colors, right? In 2007, we were at 380 parts per million. Currently, we're over 400 parts per million. So you start to see more of the pink, right? And here at 500 parts per million, there are very, very few areas where reefs are growing. And if they're growing, they're barely growing. Okay. So this continual increase in anthropogenic carbon dioxide in the atmosphere is eventually going to destroy biodiversity in the oceans. So we are overfishing the oceans. Okay. More than half of the marine fish populations are fully exploited, which means that if we keep increasing our take from these populations, they're not going to survive. It's not going to be sustainable. Harvest kind of leveled off after 1998. And if it keeps happening, we could see complete collapses like we saw in the cod industry in all of the world's fisheries. And nobody talks about it because they think, oh, it's just fish. A lot of what happened is a direct result of industrialized fishing rather than a couple guys with a boat and a line. Some of these commercial fishing methods that you're going to see in the next few slides have really, really decimated the fisheries. You get huge, huge quantities of fish, but you can't do it for a long time. Okay, so big ships and big operations are really what's caused a lot of the issue. So you need to know these different methods of fishing. So purse seining, if you guys have ever seen Finding Nemo, this is what they do at the end, you know, where they kind of like put the net down and all the fish come in and they pull it up like a drawstring. And then, you know, where Dory's in there and they all sing, just keep swimming, and they break the net. So it basically sucks up all the fish that are within the net. Drift netting sets out really long lines of net, and then they spin it around and suck it up, and you get bigger species of fish that tend to just traverse open waters in big schools rather than smaller schools like in purse seining. Long line fishing is how they fish for tuna in a lot of cases. So they set out long lines of baited hooks with spaces between their lengths, and then they pull the hooks in. Trawling is basically when you drag a weighted cone through the pelagic zone or the benthic zone. Pelagic zone is like the area where fish swim freely. So you pull this big cone-shaped net, and you just grab everything that's in the water column. Bottom trawling is when the net sits on the ground with weights, and you can see that here, and they drag it along the bottom. Okay, so different ways to catch fish. There are consequences of all of these methods of fishing. You need to know what bycatch is. Bycatch is when you catch non-intended or species during your fishing. So if you're fishing for tuna, longline fishing, you catch sharks, right? Or you catch turtles, or you catch any other kind of organism, that any other species that you weren't targeting. All right. 70% of all commercially harvested fish were captured unintentionally. And we can talk about the tuna industry in Japan when I was in high school. So I can tell you guys about that. Purse seining and drift netting capture all kinds of organisms. They pull them up and they stay submerged too long because these are air breathers, and they drown in the net, or they die of exposure on the deck of a ship, which is sad. And longline fishing is going to capture turtles, sharks, and albatrosses. Albatrosses are going to dive down, they're going to see it, and then they're going to get hooked and they're going to die. Dolphin bycatch was a big thing regarding yellowfin tuna, and that's what I'm going to tell you guys a little bit about. The dolphin population wasn't really protected until the Marine Mammal Protection Act of 1972. So anybody fishing in U.S. waters had to modify their gear to allow dolphins to escape. Not so much the tuna, but the dolphins. So we've decreased the dolphin bycatch, but I'm going to talk about this eco-labeling. But the populations really haven't recovered. Bottom trawling destroys benthic ecosystems, right? So there's your flounder, right? Before trawling at the Georges Bank, this is what the benthic ecosystem looked like. And afterward, this is what it looks like. It's a moonscape. There's not anything even remotely resembling what it looked like before, because these trawlers are weighted and they just scrape everything up. It makes me sad. So, and it's not just in U.S. waters. We can see the changes in fish populations as industrial trawling happened, as it was really introduced in the 60s. So it's caused some issues across the board, regardless of the fishery we're talking about. Technology is getting better. People are, and boats are traveling further to get their catch. So that's one of the reasons why fishing, there's been such major damage to the fishing industry. We're also fishing down the food chain. All right. So fisheries are catching less fish, but the fish that are caught are younger and smaller. So they're not going to get as much for it. And if they keep catching young fish, it's going to put more pressure on the fish population that's there, because you need larger, older females to produce more eggs. Okay. And they're also targeting other species that are more abundant, but down the food chain. So they're not the top predators. Okay. So, they're renaming fish that weren't delicious before. So if you've eaten orange roughy, okay, it used to be called the slime head because of mucus canals in its head. Nobody would eat a slime head, right? But if it's an orange roughy, oh, it's delicious. It's the same fish. All right. The toothfish, right? And I'm going to show you guys pictures of the toothfish, is Chilean sea bass now, but it's not bass. It's not a sea bass. It just sounds better than the toothfish. All right. These species are now being overfished. So we're fishing further and further down the food chain. All right. Tilapia is another one. We'll talk about tilapia. Definitely down the food chain. So one thing that they're doing to kind of prevent this from happening is they've developed marine protected areas, and you can see those areas in purple. They restrict some activities, like you can't drill for oil in a marine protected area, but you can fish within limitations. And there's only about 3% of the waters in the ocean that have that designation, but they're in important areas, the reefs and stuff. And the difference between a marine protected area and a marine reserve is that marine reserves, you can't do anything in them. It's just this beautiful area where you can go. Commercial fishermen don't like them. Recreational fishermen don't like them, but they can be useful because those fish may leave the marine reserves, the fish that fishermen want to fish for, and then they can, once they leave the marine reserve, then they can be fished by the fishermen who want to fish them. Okay, so we've got some stuff to talk about after this. Thanks for watching, and I'll see you later.